Alright, so hopefully you were able to think about how we can change the amount of magnetic field that is going through that loop of wire. So you probably thought about the most obvious one is we can just physically change where we're putting it, how we're moving it, and how much magnetic field we're actually getting within that wire. So we see if we're kind of far away from this magnetic field, there's not a lot of magnetic field going through that wire. If we bring it closer, then we do have more magnetic field that's going through this wire. So we are changing our magnetic field as we physically change the amount of magnetic field at the location of that wire. So that one's not super exciting, that's not super robust, but I don't know why I use that term, that's an odd term, but whatever. The next one we can think of that you probably maybe did or didn't think of is we can kind of change the orientation of that loop of wire. We can change how much area is within that magnetic field, how much area we're actually allowing to be within that magnetic field. So I'm going to show you a quick little example here of what I'm talking about. So let's say instead of having my loop of wire straight up and down, let's say instead I twist it so now it's facing up. So before, like, right, we had the scissors were looking like this, the loop was like that. Now let's say we have the loop that's pointing more horizontal. So the loop is parallel with the ground. So in this case, if I bring that in here, I don't have like a net magnetic field going through this wire. Yeah, I have some up on top, but it's canceled out by whatever's happening on the bottom. So I don't have a net magnetic field in this case going through this loop of wire. So I'm kind of changing how much area I'm allowing the magnetic field to pass through. So one way that you can visualize this a little bit better is if you grab a piece of paper. I don't have too much paper. I should have stockpiled some paper before I left school, so I'm using people's old worksheets. Sorry about that. This isn't yours, but still. So what you can think about is like just kind of take your paper and then blow. If we orient it so that our paper is perpendicular to the way that our breath is moving, or I guess maybe if we think about the area, if we think about the area is pointing straight up, the area is pointing directly in the direction of my breath, I'm getting a lot of breath that is hitting this paper. If I then spin it and I kind of twist it a little bit, less of my breath is hitting the paper. If I spin it so it's like completely perpendicular, so the area vector is perpendicular to the way that my air is moving, very little air is hitting that paper, very, very little. If I had it perfect, then there would be none. Then no air would be hitting that paper. But I don't have a 2D sheet of paper, so we can change the actual area of our wire. We can change the orientation. So the two ways that we're able to change the amount of magnetic field that's flowing through our wire is we can change the actual magnetic field itself, or we can change its orientation. We can change how much area is actually able to accumulate that magnetic field, how much area is allowed to pass through. So that is our new idea, and we're going to define this. So I keep on saying this term of how much magnetic field is flowing. So that's going to have, that actually has a specific term to it, and we're going to call that flux. So its symbol's a little bit odd. I kind of drew that in not a way that I like. So this is our symbol for flux, and this flux, it stands for how much magnetic field is passing through an area, so it stands for more the change of magnetic field through a loop of wire. So how much is our magnetic field changing? So we said that this amount of change is based on our area and our magnetic field. And when we're thinking about that area, we're actually going to call it a cosine theta magnetic field, because we said that that angle, that orientation, that matters. So we can write it a little bit more simply as this equals a b cosine theta. And where this cosine comes from is if we think about having a loop of wire, I kind of teased it with the paper thing, but I want to be a little bit more clear about it. We can define a direction for this object's area. We can say that the area is perpendicular to that loop of wire. So the area vector we kind of have this side view, the area vector is perpendicular to that plane. So if we have our plane of where the wire is bounded by, the area vector is perpendicular to it. So it's pointing straight up. So here's your area. We have this normal vector that is perpendicular to that plane of the area. So if we tilt this, now we are at some sort of angle. Now we have changed up, we're actually going to define it based on the horizontal. We have changed up the angle of our wire. So if we have an angle with our magnetic field of 0 degrees, so if this theta is equal to 0, then we have a maximum. We're getting a bunch of area, a bunch of magnetic field passing through it. And if we change it so that we have an angle of 90 degrees, then we have no magnetic field passing through. So let me just really quickly, here's my magnetic field. And then if my area, I may have defined the wrong angle, let's see. So if this is my loop of wire, if my area vector is lined up, if this angle with the horizontal is 0 degrees, then we have our maximum amount of magnetic field moving through it. And then if my area vector, right if here is the horizontal, if this angle is 90 degrees, then I have no magnetic field passing through my wire. That does not happen because it's kind of passing right by it. So it is based on our area. So this magnetic flux stands for the changing magnetic field within our loop of wire. It is equal to our area times the magnetic field times that cosine of theta, where our angle is based on how much magnetic field is passing through our area. All right.